ever wondered how you can actually teach a computer to, well, think? You know, how it can learn to predict something like a house price or figure out if an email is spam, all on its own. Today, we're going to pop open a software engineer's toolbox and take a look at the exact tools that make all that magic happen. Let's dive in. Okay, so here's our game plan. We're going to start with predicting numbers, then move on to making automated choices. We'll check out a really cool multi-tool called K-nearest neighbor, figure out how to choose the right algorithm for the job, and then we'll put it all together by looking at how to program this stuff for automation. Sound good? All right, first up in our toolbox are the tools for a very specific job, predicting numbers. Think things like temperature, price, or height. In the world of machine learning, this whole task has a name: regression. So the first tool we're pulling out is probably the most fundamental one of all, linear regression. The best way to think about it? It's like a ruler. Seriously, its whole job is to look at a scatter of data points and find the perfect straight line that slices right through them, capturing the main trend. So diving a little deeper, the main goal here is to predict a number. And the way it does that is by finding a line with the smallest possible error. What that means is it tries to get that line as close as it can to all the data points at the same time. Now, there is a catch. It kind of assumes your data actually follows a straight line. A classic example, predicting a house price from its square footage. It's pretty simple, right? As the size goes up, the price tends to go up in a nice, predictable, straightish line. Okay, but what if the trend isn't a straight line? I mean, real-world data is messy, right? It's not always going to be that neat and tidy. So what do you do when your data points are clearly following some kind of curve? What tool do we grab then? Well, for that, we reach for polynomial regression. Think of this as our more flexible tool. It's built from the ground up to find and follow those trends that bend and curve. Exactly the stuff our simple straight-line ruler couldn't handle. So how does it work? It's actually pretty clever. It takes your basic input, let's call it x, and it creates new versions of it by adding powers, like x squared, x cubed, and so on. That's what gives the line the ability to curve. But, and this is a big but, with great power comes great risk. The risk here is something called overfitting. This is when your model gets too good at fitting the data it's seen. It's like it memorized the answers for one specific test, but didn't actually learn the material. So when you give it a new test, new data, it totally bombs. Okay, we've got a handle on predicting numbers. So let's shift gears and look at a whole different set of tools. These ones aren't for predicting a value, they're for making a choice, for assigning something to a category. And we call this classification. And this right here is the absolute key difference between the two. Regression is all about answering how much. How much will that house cost? Classification, on the other hand, answers which one. Is this email spam or not spam? It's about picking a category, not calculating a number.
So, our number one tool for this job is called logistic regression. And right away, I know what you're thinking. Regression? Didn't we just say that's for numbers? Yeah, the name is super confusing. But trust me, even though it has regression in the name, it is 100% a classification tool. Its whole purpose is to predict the odds of a simple yes or no.
So instead of spitting out a final price, it spits out a probability. You know, something like a 75% chance that a student is going to pass their exam. The way it does this is pretty cool. It starts by calculating a score, kind of like linear regression does. But then it takes that score and runs it through this special function called a sigmoid. Imagine this function just takes any number you give it, big, small, positive, negative, and it mathematically squishes it down so it always lands somewhere between 0 and 1. And what's perfect for representing probability, a number between 0 and 1. Okay, so far our tools have been pretty specialized, but every good toolbox has a multi-tool, right? Something versatile that can do a couple of different jobs. Well, in our machine learning toolbox, that's the K-nearest neighbor algorithm. The idea behind KNN is so simple, it's almost dutiful. To make a prediction for some new thing, it literally just looks at its closest neighbors in the data you already have. The K just stands for how many neighbors it looks at. If you're trying to predict a number, regression, it just averages the values of its neighbors. If you're trying to predict a category, classification, it just takes a vote. Now, there is one absolutely crucial, non-negotiable step. You have to scale your features first. Think about it. If you're comparing houses based on price, which is in the hundreds of thousands, and number of bedrooms, like 2 to 5, the price is going to totally dominate the distance calculation. The number of bedrooms might as well not exist. Scaling puts everything on a level playing field. All right, so our toolbox is starting to look pretty well stocked. We've got some great tools in there, but a toolbox isn't much good if you're just staring at it, wondering which tool to grab for the job at hand. So, how do you actually choose? Let's make it easy with a quick choice guide. Think of this as your cheat sheet. If your problem is predicting a number, and the data looks like it follows a straight line, grab linear regression. Simple. If it's still a number, but you see a curve, give polynomial regression a shot. Need to predict a simple yes or no? Logistic regression is your best friend. And finally, if you're working with a smaller set of data and the pattern looks kind of complex and definitely not a straight line, KNN is a fantastic first thing to try. Okay, knowing the tools is one thing, but being a real software engineer is about more than just using a tool once. It's about building a proper workbench, a whole system that lets you use these tools efficiently over and over again. It's about automation. And for that, we need to talk about how we structure our code. And a really powerful way to organize your code is to think about it in 4 distinct layers. Layer 1, the data layer. This is where you load up your data and get it all cleaned up and ready. Layer 2, the models layer. This is where you keep all those cool tools we just talked about. Third, you've got the metrics layer. This one's job is to measure how good your models actually are. And finally, the pipelines layer. This is the master layer that connects all the other pieces together so you can run your experiments. So let's peek inside each one. In your data layer, you might have something like a standard scaler. That's the thing that does the feature scaling for KNN we talked about. In the models layer, you'd have your actual algorithms, like your linear regressor. For metrics, you need your scorekeepers. For number predictions, you might use something like mean absolute error, which just tells you, on average, how far off your predictions were. For classification, you'd use something simple like accuracy. And the pipeline, it just strings all these things together into one neat, repeatable process. And this is the whole point. This is the payoff. When you structure your code like this, it becomes like a plug-and-play system. You can literally just pull out your linear regression model and swap in the polynomial regression one and rerun the whole experiment with a single line of code. It makes testing and comparing your tools systematic, organized, and just so much faster. So look how far we've come. We started with just a few individual tools, and now we've built an entire automated workbench. You now have the fundamental blueprint to predict numbers, to make automated choices, and to figure out systematically which tool is the best for the job. You've basically learned how to build a machine that learns. So the real question is, now that you can build it, what problem are you going to teach it to solve?